sent PTW 32 licenses to those students who applied. So please acknowledge me the reception and download it, okay, and operation. So are you operating now? So I'll acknowledge two things. One is that you received my email with the instructions, and number two, download and operate the, okay, so this is lecture 7, I believe. Let me check. Yes, 7A. So ELE 3371 power system buildings. So what else? Do you have any questions? Let's look at the homeworks now here. So now already posted, we got these two. Let me see. Yeah, these are posted already. Okay. And they are due. Yes. Did somebody have a question? So when is it due? On Saturday? What's Saturday? The reading, which are questions. Saturday is today, so it'll be the 6th. And the problems on Monday. I think Monday. But can you open the Blackboard? Anybody? Any one of you open Blackboard and tell me when is homework TP done? Due is, I think it's going to be Monday. So Monday is going to be the 8th. Okay.
It says the homework is due on Saturday.
One of them, that's AQ. How about 7P?
I can't see 7P, just the 8.
Okay.
Yeah, 7P is not on there.
It should pop out in a moment. Okay, so then let's look at 7P. Okay, so right here. Assignments. So these are my records. Okay, so you don't see all this, but I do. So 7P here. Item is the test options. Monday. It's going to be on Monday, okay? That's what it says here. I don't know. Display after 11:07. Okay, so today is the 3rd. It'll be there in a moment because I put it 11:07. Okay, display after. Okay, here. Let me click that. Okay. So And now the student view is this right there. So now you can see, not yet. Well, anyway, I'll fix that, okay? Don't worry. Oop. Hello? Hello? Can you hear
We're
me?
here. Yes, we're here.
It looks like I closed Blackboard. Oh, anyway. So let's see. So now this is what I want to do. So let me bring out chapter 7. Okay, so let me bring out this, put it over here. So let's start with the objectives. Chapter 7. So the objectives are for protection. Realize the objective system protection, the difference between overload and short circuit, National Electric Code requirements, identify stresses, fault currents, short circuit currents, do elementary calculation fault currents, per unit method. So this is new, per unit method, asymmetrical currents, ratings of protective devices, inverse time and instantaneous response characteristics. Okay. Okay, so let's go to the next page. This paragraph, first paragraph is important. Look, nothing is perfect. All electrical equipment will fail. Protective systems cannot prevent failure of equipment. The purpose of protective systems is to remove the segment, the faulted segment, from the system as quickly and safely as possible. Then we have possible consequences. And then the mission of the NEC, National Electric Code, Article 90. The purpose is practical safeguarding. The purpose of code, practical safeguarding of persons and property from the hazards arising by the use of electricity. Okay, so a very important chapter, okay? Just dedicated to protection. So let me go back and then look at this. Abnormal conditions, overloads, short circuits, under voltages, single phasing, and over voltages. So then when you do the homework on questions, you'll be answering these questions about these topics, okay? So there are more, 6, 7, 8. They will not be considered in this book. Then here is the condition of an overload. An overload is caused by an excessive demand from the utilization equipment. So the equipment has not failed, but we put too many loads on the same contact. So then that contact plug, the strip contact plug is just overloaded. And then in the short circuit, there is a failure, an insulation failure. So now the current, the short circuit current is very high. And then here is a number which is 600%. Now, we will see that they used a lot the percentage rating. So it says overload currents can be considered to range up to 600% of the full load capacity. Okay, so if you have an equipment that it is rated 30 amps, so 600% means 6 times 30 amps, which is 180 amps. So an overload occurs when the system is being fed with 180 amps. Then here is the definition of overcurrent. According to the NEC, any current in excess of the rated current. The ampacity, and then here is a new word, ampacity. What is ampacity of a conductor? So ampacity of the conductor is the amount of current the conductor can take under normal conditions. Okay. So it's a characteristic of the system of conductors. The ampacity is how many amps can that conduct, can any of those conductors that we are looking at can take under normal conditions. So that's ampacity. Then another definition here, device. So device is a unit of the electrical system that is intended to carry but not use electrical energy. So a device is like a fuse, a circuit breaker. So it's part of the system. So here is the utilization equipment is the load utilization equipment. That's the load. So the device it carries. Okay, but do not utilize electrical energy. Okay, then mechanical stresses, thermal stresses, fine. So then calculation, okay. So then here we come at very important, which is calculation of electrical fault currents. Then I underline this. The maximum fault current for low voltage systems occur with the three-phase. Hello? Do you have, anybody has a question now?
I think he accidentally had his mic on.
Fine, so let's continue. So we have different type of faults. And one of them is the line-to-line voltage faults. There's no arc here. Okay. Let me see if here are the definition of the a voltage fault. Solid connection accidentally being made between two phases of the system or between one face and an adjacent ground metal surface. So there is extremely low resistance of the connection. The resulting fault current can be very large in the voltage fault. Now the other fault, let me go back, is right here. The arcing fault. So as a result of insulation breakdown, there is an arc. Okay. There is an arc between the two conductors, the face and the grounded, because of the relative high resistance of the arc. So there is electric resistance in the arc. The resulting fault current tends to be smaller. However, this type of fault can be more destructive because of the intense energy that is concentrated in the small area of the arc. Cope with the fact that the protective device may be slow in responding to the smaller current. Okay, so we have two types of faults in this book. Then here is the calculation of fault currents. So there are many different situations for faults. There can be face to ground, or can be two-line fault, or 3 lines, or 2 lines shorted, or 2 lines to ground, different conditions. But it says that the maximum fault current occurs with the voltage fault in the line to line. So that's the worst case scenario, okay? So then here comes a simple example. Okay, so look, a very simple circuit with the normal current of 1 amp. However, if a short circuit occurs here, then the load is being parallel, and instead of having 95 ohms load, now we have 0 ohms load, and therefore the current is going to increase from 1 amp to 100 divided by 5 to 20 amps. So this is the model of the fault. Now, we are going to see per unit values, okay? So this is the case for per unit. So let's see what they mean per unit. So here is the definition of per unit. The per unit values. So we define a base impedance which is the neutral two-line voltage divided over the rated current. Any per unit value is defined as the actual value over the base impedance. So okay. So let me show here the case of per unit. Here. So look, in per unit system, we do define base quantities. a voltage, and a power. So the subindex B is for base. Now we derive the other base quantities. For example, the current and the impedance. So all these numbers with the subindex B means base quantity. Now, we are going to work with per unit quantities. So the voltage is going to be the real voltage in volts divided by the base of the voltage. The current in per unit is going to be the current divided by the base. So for example, here, we have a generator, 100 volts. So that's a good candidate for base. We have this load over 100 ohms is 1 amp. So that's a good candidate for base current, 1 amp. Okay. So we have base voltage and base current. So now here we draw this, these two are drawn together. So this resistance is going to be, okay, so now 5 ohms divided by the base resistance. What's the base resistance? The base resistance is right here. Over 100. So then this resistance becomes 0.5 per unit. So that's what I have here. The 95 ohm resistance becomes per unit. So that's what we have here. The source voltage becomes 1 per unit. So now we can apply Ohm's law here. I per unit equals 1 over 0.05 plus 0.95 equals 1. Okay, so far this looks like artificial, but hold on. It's going to have advantages. So we are discussing per unit, okay? So we need base. Normally we start with B and S, but then we calculate I and C. And then any variable X per unit is going to be X real over X base. Okay. So that's what we have here in coming back to the, okay, so now look at this diagram. So we have, this is a very interesting diagram, okay, to look. It's a one-line diagram. Okay, so we have the utility power system is represented by a primary feeder, and that feeder has a 1% impedance or 0.01 per unit. Next, the utility transformer is 500 kVA, 208 volts in the secondary. And it says 5% impedance. Okay, so then secondary feeder, and then to the right, we shown the maybe the panel board with different loads. And then the secondary base current here. So look, I divided just to calculate the nominal current in the secondary, the 500,000 VAs divided by the square root of 3 line to line voltage. So the current is 1,381 amps. That's the nominal current secondary. So that's good enough for that's good for the base current. The the base current. That's correct. Hold on, please. Okay. No, so we are describing this system, okay? So now the one line diagram. So we assume is 1 per unit, the source. And then we will have the utility impedance. So what is this impedance? This is the impedance of all the cables from the power substation to our transformer. So if you imagine this transformer to be the transformer at the high bay here at the engineering building, and then if you imagine the power substation is going to be a substation which is located in McCall and between University, between University Avenue and Junior. So all the wiring, it's 1% impedance. And then the transformer has 5% impedance. Who makes that impedance? The manufacturer. The manufacturer will tell us, he calculates the impedance of, it's the internal impedance of the transformer. Okay, so then we represent the transformer just with this circuit. And then we have the secondary feeder and then the load. So under normal conditions, the load is being supplied by 1 per unit, which is 1,381 amps. Okay. Now here comes a fault. So at the load in the panel board, something snaps. Now the voltage is 0. Therefore, the sum of impedance is 0.5 plus 0.01, that's 0.06 per unit. Okay, so then we got a short circuit. So how do I calculate that short circuit current? In per unit is going to be 16.67. Why? I short circuit current equals 1, which is the voltage per unit, divided over 0.01, the utility impedance plus, okay, so 1P plus 0.6. Oh, sorry, let me show you this. So I made the division of the voltage over the impedance, 16.67 per unit. And this is the short circuit current right here. Okay. Now, we want to use this equation. Bring it over here. So now I know PU, and now I know base. So now I want X real, which is I, short circuit current equals, therefore is equal to I PU, I base. And that's what we have here, that equation, 1,388 times 16.67. So that's the short circuit current, 23,100 amps. Very nice. So here the very interesting point is that the transformer is represented in the per unit system by its impedance. So that's quite a fact, isn't it? That's quite a fact. So how can we do that? Let me, so look, let me have some calculations here for a simple transformer. So it's a 125 volts. So it's being fed with 125, but the transformer is 120 to 12, 50 VA. So here is the base, 50 VA and 120. So look, we pick up the base. This is important. The base at primary and secondary as the turns ratio. So this is something that we must always do. The voltage bases are not, how do you say, arbitrary. We pick up the voltage ratio. Now we can get the impedances. So impedance is equal to voltage squared divided by base. Now, there's only one base for power because we know that power in primary is equal to primary power in secondary. So we don't need two bases for power, only one. Okay, so then we have secondary base impedance is 2.88 ohms. Okay, primary base impedance, well, is going to be 288 ohms. The turn ratio is 10. Okay, now we have base. So look, here is our transformer. So let's look at the per unit base is 1.0. The per unit base of the secondary is 1.0 also. So therefore, per unit voltage primary equals per unit voltage secondary. Okay, now we calculated the currents here. The currents in base are just equal to 50 amps, what is it? Why 120? No, look. Now the base current, these are 50 VA and 50 VA. So the base currents are 0.417 and 4.17 amps. Okay. So it turns out that the currents, the nominal current over the base current for the primary and the nominal current are also equal to one another. So then we have one equation and equation 2. So from these two equations, we do write the model of the transformer. This is the ground conductor. We have voltage 1 equals voltage 2. We have current 1 equals current 2 in per unit. So that there is a transformer. So in the ideal case, the transformer is substituted by just a continuity conductor. So that's the reason, the most important reason why we use the base system, the per unit system. because transformers get so much simplification that they are just represented by conducting. This is the case where the transformer is ideal. If the transformer is not ideal, then this is what happens. If the transformer is not ideal, now what happens is that the resistance and the reactance of the transformer is connected in between. Okay. So here is the demonstration. Okay. So this is what the book has done here. The impedance of the transformer is just represented. The transformer is represented by the impedance. Okay. So this is the first calculation of a short circuit current that we have done for this single line diagram. Okay. And it's based on the representation of the transformer with the impedance. Okay. So let's move to the next. Okay. So now we are going to study the transient of the, whenever there is a short circuit current, we are now going to study the transient current. So in this very simple model, we represent the system by its Thevenin impedance, okay? Thevenin impedance with a pure inductive reactance. So when the fault occurs, this switch closes. So that's a very simple representation. How can it be done? It can be done like this. Short circuit inception, okay. So short circuit inception. It's going to be somewhere here in a system that has a lot of impedance. Possible different sources. Okay. So at T0, this switch is closes. So over, let me put here, therefore, let me erase this. So therefore we do the Thevenin at these terminals, A, B. So we put the B Thevenin, the JX Thevenin, and here is AB. Okay. So when the switch is closed, so this inductive reactance is the Thevenin impedance. The switch closed. Okay. So look. In these two plots, we see the voltage wave over here and the current, okay? So the current is lagging. Okay, so there are two two conditions for voltage. In B, it says switch closes when voltage is maximum. When voltage is maximum here, switch closes. So then current starts from zero. The current is going to start from zero, okay? And current is lagging. Now, in condition C, switch closes when voltage is at zero. So the inception of the fault occurs randomly for the voltage phase. So that's why he considered two extreme cases. So now this is the voltage wave. Therefore, the current wave is 90 degrees out of phase, lagging. But then there is a caveat here. Look at this caveat. Current cannot instantaneously change value. So that's not allowed. The current cannot jump from zero to a finite value in zero time. That's not allowed. Okay, remember why? Oh, well, it's very easy. Let's look at this. Look. It is not allowed because in an inductor, voltage equals di dt. So di dt infinity, like a sudden jump, means voltage infinity, power infinity. So that's out of the question, okay? This is not permissible. The current cannot jump. Then for the capacitor, it is the same, but now the dual is for the capacitor dV over dt infinity is not allowed. For the inductor, the current jump discontinuity is not possible. Right, okay? So therefore, this second C graphing here is not correct. So here is the correction. It's got to start at zero. So therefore, the wave form of the current is pushed up. Is pushed up. We can calculate that current. It's very easy. If voltage is equal to L di dt, then current is equal to integral 1 over L b dt plus the integration constant. Let's put an indefinite integral. So therefore, current is equal to voltage B max over L integral sine omega t dt plus C equals Bm over omega L cosine omega t plus C, the integration constant. So that's what he did here. This is C. He pushed up the current waveform. This is a cosine. It's a perfect cosine, but it's got a integration constant. Okay, so now this is the case for zero resistance. Now, if we put resistance, this is what happens. So now we have this circuit. So we need a switch. Okay. So we have R, JX, and then we have voltage here, VM, angle. So we are going to have an angle theta. Here we are going to have impedance, CR, and we have a different angle now. Here we have angle phi. Okay. So look, it says there is a DC component, look, and an AC component. So now we calculate the current. So it says there is a DC plus an AC. Now the EC has a, and the AC is got the sine omega t plus some angle here. Okay. And we are talking about symmetrical currents, RMS. So everything is RMS. So I RMS is equal to IDC square plus I AC RMS square. So when we have two components of current, DC and AC, the RMS current is calculated in that way. IAC RMS, that we know how to calculate, is just I peak over the square root of 2. Because this is the symmetric, okay. So now this is called the symmetric component. And this whole thing there is called the asymmetric component. Okay. So look at the notes, relative values. So in the vertical scale, we have vertical values. So 1.0 here, 1.0 look is the RMS symmetric. That's 1.0. Then we have the peak, instantaneous peak current occurring at 1/2 cycle. It goes up to 2.3 times the RMS. So the transient is quite strong. It's 2.3 times the RMS current. So therefore, we need to be careful because these conductors are calculated for an ampacity of 1.0 RMS symmetrical, the ampacity. However, during the short circuit, that conductor is going to be stressed up to 2.3 times the current. Okay. And you want those conductors to withstand and hold while the device, the protecting device, operates and clears the fault. Okay, now there is another note here, RMS value for an asymmetrical current of 1.33. So here is another, there are two asymmetrical currents. The highest and another one that starts at the square root of 3. And then next, if you look at the horizontal axis, now you have 5, 1, and 1/2. So that's the number of periods: 1 period, 2 periods, 3, 4, 5. So everything is being considered here a number of periods. The cycles. Now uses cycles. So example, read at the top with me. Symmetrical current is 50,000 amps. Now this is short circuit current, okay? So the symmetrical current is 50,000 amps. And the instantaneous peak current is equal to 2.3 times 50,000, 150,000 amps. Okay. What else? It says a symmetrical fault current for a X and R ratio of 6.6. Okay, so X is omega L. So this is the ratio of inductance to resistance multiplied by omega 6.6. So why is that? Because this tau here is equal to L over R. Okay. However, the book writes like this, omega t. So he puts an omega and then X over R, multiplying by omega in the numerator, and then it multiplies omega by the inductance, then it becomes the reactance. So that's the way they do it. The electrical engineers, they don't write like the electronic engineers, they write X over R. Okay, so now let's do next. So protective devices are rated as the maximum continuous voltage, the maximum continuous current, the interrupting rating, and the short time current ratings. So these are the characteristics of the protecting device. So it's got to be used in a system of voltage. So you got to be used in 208 volts or 480 or 4,160 or 13,800 or whatever, higher. So that's the voltage. Now the continuous current, so it's a device. Remember, it's a device. So it should not do anything. Normally, should just pass the current through without any action. So that's the maximum continuous current. And then next, the interrupting rating. So that peak current that we look at the diagram, that's the number 3, the maximum current that the device can safely interrupt. And then we have short time current ratings. So momentary, maximum RMS current that the device can withstand with regard to mechanical stressing. As shown in figure 6.4, the mechanical stress occurs one half cycle after the fault. This rating is necessary to ensure that the device is not physically damaged before it can operate to disconnect the faulted port of this current. the short time current ratings. So once the fault occurs, is not going to be interrupted before this peak, the first peak. The moment that the fault is interrupted is at zero crossing, maybe one cycle after, or maybe 2 cycles or 3 cycles, depending on how fast, but it's going to be when the current goes through zero. That's when the circuit breaker is going to open. It's not going to open on any other part of the current waveform. It will open only during zero crossings, okay? So that's why the rating has to be the momentary, and then we have another specification, which is the specified time. So the specified time is the maximum RMS current that the device can withstand for 0.5 seconds. With regard to thermal stressing, 0.5 seconds is divided by one cycle is 16.0167. So that's the 0.167 is one cycle. So 0.5 divided by 0.167 is 30 times. Okay. So 30 cycles. So in the long time, the circuit breaker is supposed to withstand during 30 cycles the thermal stress. At high current, everything gets hot. So then the circuit breaker should be able to withstand that. It is sometimes necessary under severe short circuits to delay the opening in order to coordinate with other devices. So here we are talking about coordination. So did you look, did you see my calculation? So we are looking at coordination. So coordination means that, so there is a circuit breaker here. And then we have different panel boards. To the loads. So there is a fault here. So the switch 1, switch 2, switch 1 before switch 2, no. Switch 2 before switch 1, yes. So that's what they mean by coordination. The timing, okay? It's clear that if switch 1 operates before switch 2, then the other circuits which are not faulted are going to be affected. And that's not allowed. Okay. So then let's go. Okay, so now inverse time characteristics. So let's read over here. The basic requirement for the detection the detection unit. So there is a detection unit in the protective device. You have the ability to react very quickly to large fault currents, but very slowly to minor overloads. So it's got to have an adaptive response, very fast and very slow. This requirement is known as inverse time characteristic. It is a desirable characteristic for the protective of most type of equipment, motors, feeder conductors, and so on, motors, transformers. This type of equipment are damaged very quickly with large fault currents, but take a relative long time to overheat with minor overloads. Okay, so here we have the reason why the device has to have an adaptive response, depending on time. So figure 6.5 shows a plot of the inverse time response curve. An ideal arrangement is obtained when the response time of the protective device is always slightly less than the point at which the equipment, let me read. Let's see. Okay, so I was reading. It is slightly less than the point at which the equipment is damaged. Okay, so here it says, an ideal arrangement is obtained when the response time of the protective device is always slightly less than the point at which the equipment is damaged. In this way, needless shutdowns for harmless short duration overloads can be avoided. Okay. So now let's study this diagram. So we have time in the vertical and current in the horizontal. So then let's look at current. Current is rated in log. So both have log scales and current in amperes. So 1 amp, 10 amps, 100. And then the first vertical line is the rated current. So this device is rated, let's say, for 5 amps. So it can conduct 5 amps for an infinite amount of time. 5 amp is an asymptote. It's a vertical asymptote. Now the time is vertically also in logarithmic scale in seconds. So the 5 amp is an asymptote, very infinite. And then we have response characteristic of the protective device, the continuous curve, and then the broken line is the thermal limit of the equipment. Okay, so then the device is will be acting before the broken line. And now we have here a second vertical line. It's very interesting. It defines the range of the overload. So an overload is defined in this diagram. Those faults with a range from the rated current, higher than the rated current, to 600 times. No, 6 times. 600% is equal to 6 times the okay, so if we said that this was 5 amps, now 6 times, this is 30 amps here. And then about 30 amps is considered short circuit. And then look at that. The time is going down. So it should respond quickly. Okay, so we're almost at the end of class. Let's see if we can see something else that's the same. Dual element circuit breaker. Okay, instantaneous stripping. Second element. Okay, so now, well, this we are going to look at the next class, and then what else? So here are the summary. And then what else? So summary, let's look at the summary. Systems must operate in a safe manner. Overloads are for short periods of time. Short circuits must be disconnected immediately. All circuits and equipment must be protected against overcurrent. Fault currents impose severe mechanical and thermal stresses. Arcing faults have lower fault currents but can cause extensive damage if not detected. Voltage faults have higher fault currents, can be quickly detected and removed from the system. Calculations are needed to ensure the proper selection of devices and equipment. Base impedance is the value of a single impedance that, if inserted in the circuit with rated voltage applied, allows the rated current to flow. Okay, so this is interesting. At rated conditions, the impedance in the circuit is going to be equal to base impedance. So therefore, this is the definition of base impedance. Fault calculations can be simplified by using per unit values. The per unit value of resistance, reactance, and impedance is equal to the actual value in ohms divided by the base impedance. The faulted current circuit must be reduced to a single equivalent impedance, which represents the total impedance between the source and the point of fault. The impedance of the power transformer is a very important factor in limiting fault currents. The short circuit current is calculated as per unit voltage divided by per unit impedance. Therefore, short circuit current is equal to rated current times per unit short circuit current. The currents that flow under fault conditions are most likely to be asymmetrical for the first few cycles. Asymmetrical fault currents increase the mechanical and thermal stressing of the system because of the transient. The rate of decay of the DC component of the asymmetrical current depends on the ratio of reactance to resistance. Protective devices are rated for the following. Okay, so that's what I have. Protective devices, let me read from the book. Protective devices are rated for the following: maximum continuous voltage rating, maximum continuous current rating, interrupting rating, short time ratings. The detection unit of a protective device should have an inverse time characteristic. Circuit breakers can have a combination of inverse time, delay tripping, and instantaneous tripping. Okay, so then these are the questions for the homework. Some of them, not all. Okay, and there are 2 additional questions in the homework, which is due on Saturday. And then these are the problems 2, 4, and 6 for problem 2, 4, and 6 for homework. Okay, so thank you all. I think we are just in time. So it was very good to see you all. Let me see your faces again. Turn on your webcam, please. Everybody here, fine. So then today is Wednesday, so we'll see you next Monday. We'll continue with this chapter. So any further questions? Okay, well, then be careful with the virus and see you on Monday. Class dismissed.
Thank you, sir.
Thank you, Professor.
Thank you.